Okay. Now, the velocity function for the first object here is going to be the slope times t plus the y-intercept. It's slope times t because what? It's a linear function. Linear function is slope times your variable plus your vertical intercept. If it's y and x, it's y equals mx plus b. M is the slope, b is your vertical intercept, or in that case, the y-intercept. Now, I say y-intercept here, it's actually the velocity axis, not the y-axis. So I used y-intercept, just a reference terminology that you're used to, but it's really a v-intercept. And we could also call that the vertical intercept, so we don't even have to specify what our variable is here. In any case, that's the linear function, and that just goes right back to what you learned in pre-calculus and in Algebra 1 courses even. Okay? So the slope 1 is 1.2 centimeters per second time, and that's times t. And your vertical intercept here is 0 centimeters per second. So we don't have to write 0 centimeters per second, it's a plain 0. So that's 12 centimeters per second times t. And a centimeter over second divided by a second, just by the rules of fractions, is a centimeter over second squared. And be sure you can make that connection, so we multiply that by t. And there's our first velocity function. Our second velocity function, just by similar reasoning, is negative 8/15 centimeter per second squared times t. Slope times t, since the vertical axis intercept of this graph is also 0. Both objects start from rest. Okay, now, gave you a rule for finding your x function if you know your t function, or your v function. And I'm not going to repeat that rule here, but this leads us to these formulas for the position function. Okay, and I mean the rule is, well, I'm going to write the rule down just for completeness. I really better do that. Okay, so if v equals at plus b, that implies x, and this is a v of t function, and x of t, but I don't have room to write the parentheses t. Then your x function is 1/2 at squared plus bt plus c. Okay, so if we look at v1 of t, a is the coefficient of t in your velocity function, and you have a 1/2 a in front of the t squared. Now, not everybody is brushed up in their calculus sufficiently, but this is just your general antiderivative of this. The derivative of this is this. The antiderivative of this, general antiderivative be this, where c could be any number, because when you take the derivative of a constant number is 0, and the derivative of this will always be this, and it doesn't matter what c is. Okay, so if we apply this rule to this function, we get this. And if we apply the rule to this function, turns out we get this. Now, the reason we have to have the 60 centimeters here is because when t equals 0, this has to equal 60 centimeters, because that's where the second ball started. Well, when t equals 0, this, being a multiple of t squared, is 0, so this constant c that we have here has to be 60 centimeters. Now, we can do that more formally, but that's the way we do it. Okay, and I asked then, when do the balls cross? Because that's what you observed. Well, when they cross is when these two functions are equal, and we just solve this equation for t. Now, in general, when you do this, you set two position functions for uniformly accelerated motion. When you set them equal, you're going to get a quadratic function, and that's what you have here. And usually, you're going to need, in the real world, you're going to just need to use the quadratic formula to solve. In this case, it's a little simpler because you don't have a multiple of t term in here, and you can solve it more easily. See that shortly.